That was a long break, huh? Hope we don't fall asleep. I got me some coffee, right? It's good for me. Okay, so what we've covered so far is to give you a brief overview, and then we're getting into more of the industry background before we go further. So, industry background, we covered the Moore's Law, which really said the transistor count goes up, doubling every 3 years, or 18 months to 3 years. And then we were starting to get into what drives the Moore's Law. It's primarily been for us technologists, we always used to look at the number of transistors and the technology node. But really, Moore's Law is more about economics. And what drives the industry is to make sure that it's more profitable for companies to transition from one node to the next. So in this next section, I'm going to give you some background to make sure you understand how that economics works. Okay? Maybe repetition for some of you. I don't know if you've seen this or not, but I think it's an important concept that you need to understand. Like I mentioned also, in my experience, I really do not say ever that Moore's Law is going to end. It is transitioning, and we'll talk about that at the end. But the industry is so resilient about finding technical solutions that I don't think that's going to end. I mean, we've got research organizations like IMEC and other places in the world that are doing leading edge research, and there are technical solutions that are available. The question is, as I'll cover in this next section, whether it makes business sense. So that's becoming more of a limiter than the technical capability. So the very basics are that if you have a chip, an integrated circuit that has some number of transistors, call it T, in one generation of technology, then by transitioning it to the next generation, you can shrink the chip size, right? Because now, if this is a 100 nanometer minimum resolution, you can get to 70 nanometers, and maybe the chip size goes from 10 millimeters to 7 millimeter on a side, okay? Something like that. So just to make sure everybody's on the same page, so this could be the basic transistor, and in a CMOS world, an NMOS or a PMOS, you might have a diffusion region with a contact in it and a gate structure. So that's what the basic transistor looks like from a layout perspective. And that then shrinks in both dimensions, X and Y, in the smaller die. Okay, so that's the fundamental concept of shrinking. And by the way, as you'll find out, as I'll tell you, up until about 28 nanometer technology, the primary motivation was to reduce the chip area, linear dimension and also area dimension. And we'll get into that a little more. So what happened then is, so let's say you are at Intel or one of the other companies, and you're working on 100 nanometer technology, going to 70, and you can make a smaller chip. Well, then people said, why not make the chip size bigger? So if you now make the chip size back to the 10 millimeter in this case, you can now get twice the number of transistors. Okay, so on the one hand, you're shrinking the minimum feature size, but with the same die size, you can actually get twice the number of transistors. And you can actually go a step further and say, well, why can't I make the chip size a little bit bigger? And now can I get 4 times as many transistors on it? So again, this very simple concept was repeated over and over and over. In reality, the process people, if you're a process expert, what you're limited by is what's the smallest feature size you can print as one constraint, It's also the minimum size contact that you can open. It's also limited by how close you can bring two lines. And maybe Core will get into that more detail tomorrow, but it's all of those constraints that limit you to a set of what's called a design rule set or a design manual that if you go work at TSMC or SMIC, they will have a set of design rules for 28 nanometer, 22, 16, 14, whatever. Those are guidelines that are handed to the designer so that you can design your digital chips, your analog chips, whatever, based on those physical design rules and guidelines, which represent limitations in the process area. And you also have a set of electrical models, like Professor van der Spiegel was saying, that determine the device characteristics and the circuit characteristics of devices built on a particular technology. So those are the basic elements: a design manual, a set of manual models, and a way you can go as a designer, and that's all you need to move forward and do your designs. Okay, so fundamentally what you're doing is process guys are saying you can shrink the minimum feature size, you can build smaller transistors, and the designers are saying, well, we're going to build, there's also limitations on, by the way, how big a chip you can make. And so that's what limits you to the maximum die size. But this is how you get from 2x to 4x number of transistors. Questions? So physically, to explain this, how many of you have been to New York? Manhattan? Anybody? Okay, so this is a map of Manhattan, New York City. That's where the World Trade Center used to be. And that's laid out really in a very grid pattern. There's avenues going this way and streets going this way. And I just wanted to illustrate that if these are I turned it a little bit, so these are the avenues going up and down, these are streets going this way. And now if you were magically to be able to shrink the whole size so that now in the same 8 avenues, now you can do 15 avenues, then that's the shrinking principle, right? If you have a basic track set in one technology like that, and now you shrink it by 30%, you can put more tracks in there. And that's how you get more transistors. So it's just a physical illustration. Again, so make sure we're all on the same wavelength. The cross-section now of a transistor looks like this, very simply said. You've got a surface of the silicon that has 2 drain and source regions, which could be N+ on a P-type substrate, a gate oxide, and a gate oxide, and then the metal gate or a polysilicon gate on top of that. So some definitions: the minimum feature size for the longest time used to be defined by the minimum length of the gate that you can have. Call it an L. Well, that's the physical gate length, but then there's also the electrical gate length, because there's a depletion region associated with the bias that you provide on the drain to the substrate, and so that reduces the effective channel length of the device. So then when people started to shrink the minimum feature size down to a level where, on the limit, if it's a really long gate length, then the delta between L and L effective was pretty small, and people still, in the 1.5 micron days, for instance, that's the nomenclature of the technology, was 1.5 microns. When you're getting down to deep submicron or 90 nanometers, then this difference between the physical L and the effective L becomes quite significant. So for competitive reasons, many suppliers started to cheat a little bit and said, well, instead of a 90 nanometer, I'm really doing a 70 nanometer, whatever the number, right? And to attract business into the whole thing. So I'm just pointing this out as the transition of how the technology definitions have evolved. And I'm not covering every piece of it, but that's the whole idea. So people went from minimum melt and L effective to what's become more standard is to look at the pitches. So what really matters is not just the length of the poly, or width in this case, but it's the combination of the poly L and the spacing. And if that's the total pitch, after providing a little contact in there, and you take half of that pitch. So that half pitch then becomes more of a standard that you can't really cheat in that. So that's become more of a standard. It was kind of driven by the ITRS. The roadmap for semiconductors is starting to define that. Again, so we're all on the same page. If you're looking at a 20 nanometer technology, and that's the minimum L, you can fit 50,000 of those in 1 millimeter, and that relates to 2.5 centimeters in an inch. So just to give you an idea, sometimes I teach classes to people that haven't been through this. I don't know if you've seen this or not, but just so we are all on the same page. Okay, so historically, as I mentioned to you, the Intel introduced the first microprocessor, the 4004. It actually had 2,300 transistors on it, 2,300. And it looked like this. This is the package, had 16 pins on it. It's, if you notice, it's called a DIP, it is dual inline package. And in those days, the computer manufacturers would have on the printed circuit board little holes that go through the green board, and this device would fit right into the 16 holes where the feet were, and had a cover here. So that's the original 4004. Devices today are 10 billion type of transistors. So lots of changes that have occurred in the industry since then. Here's a picture of the Intel Core i7. I think Jan said he just bought a laptop, Apple laptop with Apple MacBook with the Core i7. I don't know if this is the same generation or not, but here's all the 1,000+ pins, leads. In fact, lead is sort of a misnomer because these are actually landing pads that get soldered onto the board. But you can see that it's a pretty complicated device. So in here sits the chip, and then there's the external package. As we'll get into the packaging section, the purpose of the package is to two or three purposes, right? One is to mechanically protect the chip, because the silicon chip is very brittle, and to provide the external connections, electrical connections. And the third piece is reliability, because you don't want the chip exposed to moisture and other environmental conditions. So anyway, that's the chip. If you look within the silicon itself, in this case it's quad core, so there's 4 cores, has a basic shared level 3 cache, a memory controller, I/O, and other functionality. Pretty complicated chip, right? That then goes into a laptop, which has a motherboard, has a heat sink associated with it, and a little fan that blows cool air. And like somebody says, about 10 watts, 10 to 50 watts, depending on the particular processor. By the way, here's a design question. Do you know what fraction, I'll give a hint, what fraction of the Intel processor is asleep at any given time? That's a hint that says there are transistors that are not working, they're asleep. Any guesses? 50% of the transistors could be doing nothing and falling asleep. When there's a demand comes in to do a floating point operation, that floating point unit wakes up, does the calculation, and goes back down to sleep. How do you think that happens? Some designer designed that in. There's an algorithm in there. And what's happening is that over time, as the leakage current increases, it's very difficult to manage the power dissipation to stay low. So there's all kinds of tricks that people play. So if you were a digital designer, it's supposed to be a boring job, but guess what? This is not a boring job. This is a pretty important, significant improvement and enhancement that Intel's made. So that's just one example. It's a combination of software and architecture and the design that pulled together helps out the process people and therefore allows Intel to ship the chips. By the way, do you know what the power dissipation of a CMOS chip is? Does anybody know the formula? CV square F, right? Capacitance, voltage square times frequency. So when we're buying laptops that are going from 2 gigahertz to 2.5 gigahertz to 3 gigahertz to 3.5, they're little numbers, but for the designer, it's a tremendous challenge, right? Increasing number of gates, therefore capacitance going up, frequency is going up, power dissipation keeps going up. That's the reason why you have to manage the power or dissipation in active chips. As I mentioned, for a smartphone, the next processor I'm going to show you is a Qualcomm Snapdragon, for instance, right? Still operates at 2 gigahertz, probably not as much as not as fast as the Intel chip, but similar number of pins, external leads, but the power dissipation is 2 watts maybe at most. Because like I gave away the answer, right? This thing cannot be very hot in your hand or you're not going to be able to hold it. Now, here's a question. So the orange is the backside of the chip. Anybody have an idea why there are pins on the top? You have no idea? I will show you an example. What happens is when Qualcomm ships a chip, whoever the customer adds a memory chip right on top of the logic chip. And again, I'll show you an example, but why do they want it right on top? Any guess? Dynamic memory is really close to the processor, means the performance is better or worse? It's better, right? Because you could have it on the side of the chip. Now you got to have connections through the PC board to the processor every time it talks to the memory. This way it's right on top. So connections from the memory to the logic chip are very short. Little tricks of the trade, right? Okay. Intel does the same thing, by the way. Maybe not right on top the way they do it, but they want to get close proximity. Intel chips, because they dissipate more power, and AMD, same thing, right? Higher power chips, they have to have heat sinks. That means the way it's packaged in the package, you got to have an external metal heat sink attachable to the chip, which means if you do a flip chip, then the heat sink has to be on top. It's on the bottom. I don't know if you noticed, but this thing here is a bunch of thermal balls that help take the heat out of the chip. Somebody has to design all this. You have a packaging engineer, you have to worry about mechanical, thermal, reliability. If you're a process engineer in the packaging area, you got to make sure those balls don't fall off over time, right? And all kinds of reliability constraints. So extremely exciting field to be in. It could be more mundane than being an analog designer, but somebody needs to do it. And when Professor Wei says China needs 3x the number of engineers in the semiconductor space, they're not all designers. They could be manufacturing engineers, they could be packaging engineers, reliability engineers, quality engineers, all kinds of spaces. So keep that in mind. And again, as an entrepreneur, if you're trying to solve a problem, then figure out where it's going to fit in and who your customer is going to be, right? Okay, so that Qualcomm chip looks sort of similar. I mean, they got in this case, a ARM core processor. They got graphics unit on there, a bunch of logic, and so that's what ends up kind of a boring little chip, right? A couple billion transistors on it. So here's a comparison. It's data from Intel, from Bill Holt. He was the executive VP at Intel. I think he just retired. He was showing that in 1978, if you opened up a chip, an Intel chip, the little contact that has to be made from the metal to the silicon might have been about 5 microns on a side, because this is 1 micron marker. So this is 5 microns on the side. Today's, well, in 2011, so 6 years ago, this is 22 nanometer technology. In this little 1 square micron, you could fit in 10 static memory cells. That kind of gives you an idea how the technology has evolved. This was my kind of business when I was the process engineer, this kind of dimensions, and what this is now is at the beginning. I mean, later on it was a lot tighter. But here's a comparison between the 4004 and 14 nanometer devices, the Intel 6th generation processor. Wafer size is probably gone from 2-inch 50 millimeters to 300 millimeters. That's the ratio of the area. The technology node is 700x. Performance is 3,500 times. Price per transistor is 60,000 times less. That's the driving force why they were using it. And then transistor energy efficiency, that's the other reason why they're using it, is 90,000 times. Energy didn't used to be a big factor initially. It was all about performance. But as the power dissipation started to get up there and battery power was really important, especially in these IoT type applications we're going to talk about, energy becomes a real strong consideration. So the industry has really been a very exciting place to be, which is the reason I say it's been so exciting looking back. But my purpose in showing all this is that looking forward is also very exciting. It's not just about scaling transistors down, but it's about making solutions that you can help make. Okay, so this is again from Bill Holt's chart. Professor Van der Spiegel and I read the same information from ISSCC, is the major solid state circuits conference, and I think number of quotes that I have are from there, and he was quoting from a number of those papers also. So here's the same information that I was telling you about, the 32 nanometer chip. You shrink to the next generation technology, it would be 22 nanometer node. Chip gets smaller, but they actually raise the chip size again back to the same to get 2x the number of transistors in the same area. And you shrink the green again to 14 nanometer, which is the next node, multiples being about 0.7x. By the way, this is all run by what's called the Dennard law. Dennard proposed in 1974 a paper that talked about linear scaling, and that's been the big driver for Moore's law for the first 30 plus years. So here's the 14 nanometer going to 10 and 7 and 5. So the fundamental idea is that the same circuitry fits in half the space, because 0.7 times 0.7, and twice the circuitry in the same space. So the blue is again the 2x. Remember I showed you that simplified summary before. And then what they do is they optimize the design to take the best advantage of the new technology. In the old days, it was just about the technology linear shrinking, but then as I'll show you, there's more features and more materials, optimizations, and so from a process perspective, and then the design had to match those to take the full advantage. So this chart again shows you a similar type of picture that says 130 nanometer to 90 to 65 to 45 to 32 to 20. By the way, I'm skipping one in the middle, and the reason is that these are the major nodes, the 130, the 90, the 65. What's in between are like 10% shrinks that as the foundries started to get in the business, they were trying to capture some business that once you have a design done in 130 nanometer, they could get performance enhancement and a little cost reduction by doing an optical shrink. Optical shrinks really had a limitation, but it was easy to do in that you could take a database and just when you're writing with an E-beam, the mask, you just tell the beam to be 0.7 of the original or 0.85 of the original one, and you get a much smaller line dimension. So there's tricks like that that people were playing. So initially, for many years, the Moore's law was really all about lithography and Dennard's ruling, linear scaling. What that gave you is better density, more transistors per square millimeter, you got better performance, and you got reduced costs. So that was the big driver. Then around the 90 plus nanometer node, it started to be that you had to make some changes because now there was starting to get leakage in there and other constraints that maybe Corey's going to talk about tomorrow. And so you had to introduce new materials like strained silicon and high-k metal gate. And then at about 28 nanometer, even that was starting to have some stress and limitations. And so people started to look at what's called more than more type of technologies, and we'll talk more about that as a set of opportunities for packaging three-dimensional on the silicon as well as in the package. Another limitation, if you stop and think about this, for the longest time, the power supply voltage used to be 5 volts.